All right, thanks everyone for coming for this breakout session on the Docker technology track. We're going to be talking about storage for containers. I think there's going to be a bit of a Kubernetes focus here. We have two presenters who are working on exactly that area. There is Anusha Ragunathan and Anshul Pandey. They're both engineers at Docker. Anusha works, I think, as a maintainer on the Moby project. She she was the original author of the Docker plugins framework and is working on storage integration with Kubernetes right now. I think she loves performance analysis, low-level geeking out stuff, and I think she'll talk a little bit about it as you see through the presentation. Anshul is a lead software engineer. He is mostly into distributed systems and says he likes social psychology, and I don't know what he was referring to. He'll probably answer that during the talk. To the speakers now. Thank you.
Cool.
The notes are here.
All right. See you in a bit. Right. Cool. Hola, Barcelona. How's everyone doing? Good? Enjoying the tapas this week? A little bit? Two guys? Cool. Who here has used or experienced storage in some way working with containers? Show of hands. Good sizable amount. So you could probably identify with this sentiment. Container storage is a bit of a scary topic. And so here we're going to basically provide some therapy for those who have been traumatized by this topic. Quick disclaimer, some of the things that we'll demo today won't be available in GA form right now, but will be available as a tech preview later. Containers are ephemeral, but storage is not. What's going on? Sorry. OK, there you go. Cool. And if you've deployed storage on containers, then you know storage is hard. And for containers, it's been kind of an afterthought. Initially, containers, when they came about, they focused on dev and test workflows. And persistence was kind of an afterthought. So you would create new containers for your workflows. You would run your workflows and then throw them out. And it was quickly realized when the focus moved to production that persistent storage is going to be very important. The other challenge is that the storage ecosystem is huge. You have, first of all, many different orchestrator platforms. And each of those platforms comes with a separate set of specifications and APIs. The specs themselves are constantly evolving. There's many different storage backends available, and your favorite backend may or may not be supported. So that's where we are right now. We have all these different orchestrators to choose from, and each of them has its own set of specs. So it's easy to feel lost. Furthermore, as a storage admin, your life is really hard. Because a key requirement that enterprises have is that the developers should be able to access storage without worrying about how it's implemented underneath. So if you're a storage admin, this is a typical day or typical life that you will live. You'll begin by understanding the use case, followed by mapping the use case to the right set of tools. And once you lay that groundwork, you will then, on day 0, provision volumes, and then very soon after deploy your apps, attach those provision volumes to the apps. And very soon you'll have to think about high availability and disaster recovery to make sure your apps are highly available and resilient. So in the first part of the talk, we'll focus on that, laying that groundwork. and we'll go through a quick storage primer. We'll talk about characteristics, protocols, and use cases for storage. Starting with container platforms and the different options available, focusing on Docker Enterprise here. You have a choice of orchestrators. You have Kubernetes, which provides high scalability, auto-scaling. And for storage, you have options like in-tree provisioners. You have external provisioner, you have FlexVault, and you have CSI, which is something new and was recently announced as GA. And so you can see on the kube side, the ecosystem is, the storage ecosystem is quite fragmented. You have all these different options. We'll talk more about that later, how that affects things. On the Swarm side, you have support for production. You have production support for Windows, and you have Docker Volume plugin to use as a storage stack. And all that sits on top of the storage engine backend of your choice. Quickly talk about different storage types, and we'll talk about file, block, and object here. Starting with block, the data here is arranged in well-defined blocks, which are identified by offset and a range. And the metadata itself is not stored with each block. There's a layer on top which provides the metadata management. File storage is very similar, but the data is arranged in files in a hierarchical fashion like a file system. On the object storage side, the metadata is stored with the individual block, very similar to block, thus creating an object. And each object is individually accessible. Let's look at these different storage use cases for the types that we just discussed in the previous slide. Starting with block, the fit here is high performance primary or secondary storage with medium term storage and medium amount of data. Latency requirement is typically very low, and the typical examples are transactional or relational databases. For file, it's typically capacity-based secondary storage. The amount of data tends to be somewhat lower, and you trade off latency for simplicity of access and use. Examples, unstructured data for archival and discovery. And finally, object storage, which is highly reliable cloud scale, primary or secondary storage. And the amount of data tends to be high, latency low to medium, tending to be on the low side for more modern applications, mainly unstructured big data applications. So we looked at how you can, starting from your use case, identify the different characteristics of the use case, starting from your application workloads at the top, and map those characteristics to data properties like latency, IOPS, et cetera, and then finally map those to a storage type, and finally to a storage backend of your choice. So you could use different storage backends, software-defined storage backends, or more enterprise appliances. And that was kind of an overview of how you can lay that groundwork before you actually start deploying storage in production and start deploying your apps. And to now take a look at the rest of the lifecycle on how you can actually deploy storage with a focus on kube and deploy for availability and for resilience, I'll hand it over to Anusha. Good luck.
I'm going to stand on this side because I don't have a clicker. Hi, everyone. The rest of the talk is going to focus on storage on kube and how Docker integrates really well with kube. So just feel from the audience, how many have Kubernetes deployed in production? Oh, wow, that's a good number. How many of you use Docker EE to do that? Not very many hands. So one of the reasons why we are giving this talk is to actually show that Docker is very committed to being a very good kube distro. We are following the SIG storage community very well. I've had several hands hallway tracks with over the last 2 days. I have one after this session as well, where we can actually talk about your requirements and sort of take that back to Docker and make the Docker EE platform the platform for kube distros. So having said that, I'm going to focus on 3 pillars of storage, provisioning, high availability or HA, and disaster recovery specifically for backup and restore. Before digging deeper, some jargon around kube, because I see that a lot of the audience is still not adopted to kube, so this is sort of like a primer. Pods are basically a collection of containers that work together to represent your workload. Persistent volumes, or PVs, are basically a representation of a piece of storage in your cluster. And the lifecycle of a PV is independent of the lifecycle of a pod. A pod can be started, rescheduled, stopped, and removed, but the PV stays alive, and it's managed very differently. A persistent volume claim, or PVC, is a request to access that piece of storage. And just like how pods consume compute and memory, PVCs consume storage resources. And just like how pods can request access to different number of CPUs or specific CPUs or different levels of memory, a different amount of memory, PVCs can request access to the different sizes of storage, different access modes, and so on. And a pod typically ties to a PVC for accessing storage. Now that we have that out, let's talk about the first pillar, PV provisioning. Before I jump in there, we talk about persistent volumes. There are also these concept of ephemeral volumes in Kubernetes, which are not persistent. They basically live and die with the pod. Typically, you use that for TempFS secrets and stuff. So this talk is more on PVs. There are 2 types of provisioning that you can do, static and dynamic provisioning. And we're going to talk in detail about the lifecycle workflow of dynamic and static provisioning. But at a very high level, static provisioning is where you have a set of pre-created volumes and the pods use them. Whereas in dynamic provisioning, it's on demand. It's based on user claims, and they're not pre-created. They're created when there is a claim. Dynamic provisioning is primarily achieved through this concept of storage classes. Typically in the industry, you also talk about storage tiers, gold, silver, platinum, where you have different SLAs for your storage. You tier them up based on different performance characteristics, IOPS, latency, value add features such as backup, restore, encryption, so on. So you, as a storage admin, you can actually classify your storage using these storage classes and back it up with a provisioner. So what is a provisioner? A provisioner is basically a piece of code that provisions PVs. And there are 2 types of provisioners. There are in-tree provisioners that live in the kube repository, and they are in process with a kube process. And an external provisioner is basically a piece of code that lives outside the kube repository, and they run outside, or the process boundaries, basically they're running as their own independent processes. The kube API objects that are primarily involved in PVs are persistent volume and persistent volume claim. So if you want to I just put that up because if you want to look up more on, if you want to Google it up, you can basically use that. We're going to go through workflow. This workflow has 2 personas, a cluster admin that actually makes sure that you have volumes available, and a developer trying to use those volumes. So our cluster admin is, in a static workflow, she's trying to pre-provision all the volumes and register these PVs as part of the cluster. Now, as you see, there are a pool of persistent volumes here, and they're each backed by a different storage provisioner. You have NFS, iSCSI, and AWS EBS PVs. So it just shows the variety of PVs that you can have in your cluster, and Kube actually supports all of them. In fact, almost every storage provider is working with Kube to make sure that the workflows are possible and quite straightforward. Now you have the developer coming in trying to actually access those PVs. How is he going to do that? He claims a PV by writing a claim YAML file and references the PV. At this point, Kube master it has a controller loop that looks for the incoming claim and does a match with the existing set of PVs. Now, once this match is done, the marriage happens, and it's a one-to-one mapping. A PV and PVC cannot be mapped to anything else. The developer now references this claim in a pod. That's actually his workload. Then the Kube controller actually inspects the claim and mounts the PV into the pod. At this point in time, the pod is ready to start using the PV. But you can see that this is not very efficient because the cluster admin has to pre-create all these volumes of a specific size and also of a specific backend, and you don't know what kind of claim the app developer is going to come up with. So also the size requirements might be different. The app developer might come in with a 50 gig claim request for a NFS pool, while the cluster admin could have created a pool of 100 gigs, and so it's very wasteful. And so the match never happens, and then the controller never binds the PV and PVC. So the recommendation is to go with on-demand provisioning. We'll see a workflow for that. So again, our cluster admin is here, but instead of creating PVs, she creates storage classes. In this specific case, she creates 2 storage classes, slow and fast. Slow is backed by a provisioner that's provisions just regular hard disks, whereas fast is backed by SSD drives. Let's see what a developer wants. He wants to provision fast storage. So in his claim YAML file, he's going to refer to the storage provisioner as fast. Now the controller provisions volumes on demand. He looks at the fast storage class and maps it to the corresponding provisioner, and now we have SSD persistent volumes in the back end. The controller now binds this new persistent volume to the PVC. The marriage again happens here, and the rest of the workflow is very similar to what we saw in static provisioning. The developer references the claim in a pod, and the Kube controller basically inspects the claim and mounts the PV into the pod. We are going to see a demo of this. What you see in the demo is basically a 3-node cluster. We're going to have a Kube master and 2 workers, and an external iSCSI target server. And the 2 workers that you see here will serve as iSCSI initiators. And they're basically configured to actually talk to the iSCSI target server. The thing is, I ate a lot of grapes this morning and skipped lunch as well. So hopefully this works. Let's see. So let me pull up the UCP UI. Okay, so this is the UI for the 3-node cluster that I have. All right, so I have a script. Once this passes, I will explain what the script does, or maybe it's going to take a while so I can explain. What it's doing is it's provisioning an external iSCSI provisioner, and it's creating a storage class. It's also creating a claim. Let's look in the UI. So that's the iSCSI provisioner. Let's look at the storage section. We have the storage class for iSCSI. We have a claim. This is it's a small claim. It's a 100 meg claim. And you see that once the controller was able to provision the volume, it was able to bind the PVC. This is the PVC, iSCSI-claim is the PVC, and this is the actual persistent volume. So we just dynamically provisioned PVs out of an iSCSI backend. Now, we're going to define a pod to use that volume that we just created. So if you go to the pod section, we're seeing that the container is being created on node 2. Let's look to see. Oh, yes, the demo worked. So we can see that it's actually the volume got attached to the node, and then there is a mount that happens, and the container started running successfully. So we can actually do a kubectl pod describe of the pod. This is the one that it's actually a replica set. So it's running on, the pod is running on all the nodes. So if you see the mount section, so this was our pod trying to mount the iSCSI volume, and it actually succeeded successfully. So that was the first demo where we dynamically provisioned iSCSI. Going back to our presentation. The second pillar we're talking about is high availability. High availability involves handling both node failures and storage failures. We're going to specifically talk about how node failures are handled. There are two types of node failures. One is when you have an intentional node maintenance, and you have to sort of drain everything in the node, and then if things get rescheduled and volumes get detached from the node and sort of get attached and remounted. And the other part is node failures that are unexpected, where the node comes crashing down, or there's a kubelet crash, or there is a communication issue between the worker and the master. Kube actually provides inbuilt support for node failures. There is the attach-detach controller that's running on the kube master that is in charge of talking to the provisioners running on your nodes, and they move the PVs across the cluster. The attach-detach controller works very closely with the node controller in the kube master to determine the state of a node. Now, if the node does not send heartbeats for about 6 minutes, then the node is sort of declared as down, and the PVs are relocated to an appropriate worker in the cluster. Now, if such delays are not tolerated in your cluster, then the recommendation is to use a software-defined solution. In a software-defined solution, typically you don't have you have sort of commodity servers that pool their storage resources and present volumes up the layers. And typically replication is a big part of this solution, where the volumes are sort of replicated from the beginning. They're replicated, they're synced up. So in an SDS solution, the attach-detach happens almost much faster than regular traditional storage, where you have to mount and unmount. We're going to show our second demo. In this demo, it's the same setup, but I'm going to simulate a maintenance of our worker, and hopefully we will be able to see that the PV actually gets relocated to the other node. So for this, let's see what the pod is running on. So the pod is running on worker 2. So let's see, so we can, what we're going to do in the script is basically just do a kubectl drain of that node, simulating maintenance. Let's see what the UI is saying. Yeah, okay, so it says that it's terminating the pod on the first node, and then it's scheduled it on the second node. Let's look at the event log. So you see this multi-attach error. That's very typical, don't freak out. It's basically trying to warn us that the volume, the database hasn't updated yet. So basically, iSCSI volumes cannot be attached for writing by more than one node. It's an exclusive request for access. So that's a temporary one, because then the first node sort of relieves the lock, and then the volume gets attached to the second worker. So we just have to wait. Yes, okay. So we've been able to attach the volume successfully. And yes, the pod is running. So we started, what did we see in this demo is basically we simulated a failure on node 2, and where the PV was attached, and we saw that we were able to, the pod was rescheduled on another node, and the PVs got attached and mounted, and the pod is running successfully in the second node. So that concludes our second demo. The final pillar that I'm going to talk about is snapshot and restore. Backup is a very important operation for storage admins. They need the ability to back up data from snapshots and restore from them whenever desired. This requires coordination between the orchestrator and the volume snapshot capabilities provided by the backend. And there is no native support for backup restore in Kubernetes. The support is implemented through CSI. This is the first time we're talking about CSI in this talk. CSI is basically Continuous Storage Initiative. It's a way to standardize storage specs across different storage providers. We're going to talk more about it later. But at a high level, it's the future of storage in Kubernetes. And support for volume snapshot restore is implemented using an external snapshotter. Just like we had external provisioners, we have an external snapshotter process running outside of the kube process, outside of the kube tree. And it invokes the plugin APIs. And the snapshots are created, so even the core, even the API object that gets created during a snapshot. So you have a volume, you have a persistent volume, and you're trying to take a snapshot of it. The object that's used for creating that volume snapshot is not even part of the kube core APIs. It's actually implemented as a CRD object, like a resource definition object that's not even part of the core kube. So you first have to deploy the CRD object. And the restore is actually driven through a persistent volume claim with the data stores pointing to it. So when we go through the demo, you will understand this more. I can show you the YAML files for that. So we're going to the final demo. Here we have just a 2-node cluster. And we have a master and a worker. They are both running on GCE. GCP is basically one of the first implementers of CSI because it's Google owned, and Kubernetes is basically heavily influenced by Google. And they also have the backup restore controller working very well. Their plugin supports it. So we're going to show how PV can be snapshotted. And the same, so the way the PV snapshot object is created, and the restore is using the snapshot object as a data source. And finally, we will show, what I'm going to show is actually simulate a data corruption and show that, that we can revert back to we can restore the data by using the stored snapshots and create a new pod for using the PVCs. Let's go to the demo. So this is my GCE-PD cluster. And I'm going to have to type in a whole bunch of things. I'm just going to copy paste. So before that, let me show you. We have an Nginx web server that's actually running. And this web server has an index HTML that says hello from Barcelona. And we're going to basically corrupt it. But before we corrupt it, we're going to take a snapshot. So let's take a snapshot. Let's look at what that snapshot file YAML is. So what we did was, we're not provisioning anything from scratch. We already provisioned a bunch of PV and PVCs. We are just using whatever was already provisioned. And we're pointing, so this is of type volume snapshot, and the source for this snapshot is a persistent volume claim that was already created. So this is the volume snapshot claim. And let's see. So that's our volume snapshot. Let's look at whether the snapshot is done. You can grab, yeah, so it is done. Now let's simulate the data corruption by writing some junk to the HTML. So now when you look at it, the HTML is serving foobar instead of hello from Barcelona. And let's do a restore. And let's see that a new PV got created, and we should have a new PV created and bound to the PVC. So let's get the status of PVC. It still says pending. Okay, it's bound. So now that it's bound, we can actually create a pod using the restored PV. It's similar to basically rollback. Now let's see if we can curl. Oh no, not this one. We created a new pod. Yes, so we were able to restore the data and create a new pod using the restored volume. So let's go back to the slides. So what I just showed you is not, again, all of the demos are not available as part of Docker EE today, but will be available in an upcoming release. What I showed you as far as backup restore is very tightly integrated with kube's CSI support. And Docker is very committed to following up and tracking kube features and kube releases closely so that we can provide our customers with the latest and greatest. To talk more about CSI, I invite Anshul back on stage.
Cool. Thank you, Anusha. That was great. So, yeah, give it up. Thank you. The reason we wanted to show you these demos today was because, well, two reasons. One, obviously, we wanted to walk you through the life cycle of a typical storage life cycle. But secondly, like Anusha said, we wanted to highlight how Docker is making storage a priority. And we'll talk more about that in following slides. First, let's talk about Container Storage Interface, or CSI. And if you know CSI, you know that it's becoming a big deal. Oh, you got to switch it.
I think it's 2.
Right. Oh, yeah, I could just do that too.
Now you have to switch. Okay.
So, Container Storage Interface is an industry standard that enables the build one, use many approach for storage plugins. And the idea is to unify the fragmented storage ecosystem into a single standard. We previously talked about how there's many different options available for different individual orchestrator platforms. And the goal with CSI is, the reason that CSI was created to create an orchestrator independent standard, which will help us unify all of those different specs into a single spec. The reason that CSI is a big deal is because it's a platform independent spec. So it's not controlled by a single storage company or an orchestrator platform. Furthermore, it's a simple community-driven approach. So the goal is to provide, when it started out, the goal was to provide, to address more basic use cases like provisioning, and then moving on to more involved use cases like application consistent snapshots as the spec evolves further. How will CSI change your life? One of the reasons is the simplicity of the interface. And if there's one thing that developers dislike, is to be locked down into a single standard, because that's the only one that works with a given orchestrator platform or a given set of tools. With CSI, organizations won't need to choose the container platform that they want to work with, because the storage only works with that platform. So you can work with Swarm, you can work with Cube, you can work with Mesos. And that'll help bring storage to the container masses. So how is Docker involved with CSI? Like Anusha said, we're actively tracking the CSI integration, and CSI was recently GA'd in Cube. And I'm happy to announce for the very first time that Docker will support production-grade CSI support in a release very soon next year. Docker also recognizes the importance of the movement and is not only committed to bringing CSI in the platform, but also is actively contributing code to the CSI subproject within Cube. So hopefully we're feeling a little better about this. And like I said, Docker is very committed to building storage and providing better storage support in the platform. To summarize, storage is hard, but it can be managed by carefully understanding the use case, mapping the use case to the right set of tools, and to finally deploying fault-tolerant and resilient applications and resilient storage, which can easily be used by the storage, by your organization, the developers in your organization. And to highlight again, Docker is very serious about storage and is making it a priority. Lots of new things are coming from Docker in the field of storage, including the iSCSI support that Anusha demoed previously, and of course, production-grade support for CSI. And we're here to help you, to walk you through this journey, to help you understand your use cases better, your requirements better, and recommend best practices. I will encourage you guys to take the Breakout survey and also get the Forrester report on container platforms on this link if you're interested. If you're interested in migrating legacy Windows apps, we can help. And here's a link that helps you find out how. And we look forward to seeing you all next year in San Francisco for DockerCon 2019. So thank you for coming, and thank you for listening.